Okay, it had all the important components which actually went into the proofs of these theorems, but it was not completely correct mathematically. But this is the Ito's formula which we derived. So we considered a function phi, which is a member of CC infinity of 0 comma t. This is a closed bracket, where so it doesn't have to vanish at the endpoints of time of RD. This goes to any real value. So we had phi of t comma xt minus phi of 0 comma x0 is given by this nice integral. Okay, so when we thought of just flows like ODEs, we did not have this second order term, the Hessian term. We did not have this Brownian motion martingale term. We just had the first two terms, and we called that the continuity equation, or in some sense. Okay, so now we want to derive how the probability distribution evolves along this trajectory, right? And this is what is called the Fokker-Planck equation. Okay, so just like ODEs had continuity equation, we'll derive the Fokker-Planck equation, right? So okay, so let xt be distributed as pt, that's some density. So what can we expect this to obey, right? So I mean, last time we had a first order ODE here, so therefore PDE here, so we kind of expected this to be a second order kind of a PDE. So we expect this to be sort of a second order kind of a PDE. So how do we derive this? Okay, so what did we do last time? We actually went into CC infinity with the open brackets here so that the endpoints vanished. Okay, so rewriting the Ito's formula like that and taking an expectation over both sides, I'll actually drop the internal variables here, and so that it's easier for me to write. So let me ask you a simple question. If I take an expectation of this, what is it? Yeah, why is it 0? Correct. So it is dbt is 0 because we are considering the Ito integral. It is not 0 in general, but because it is Ito integral, it is 0. Okay. So if you take the expectation, this goes away. Okay. So we have an expectation over the next three terms. And if we consider phi to be CC infinity, which vanishes at the endpoints, right? So then this term would also be 0. Okay. So let's write the Fokker-Planck equation now. So for all phi belongs to CC infinity of 0 comma t times RD. See that these are open brackets, not closed brackets, right? So so this vanishes. Taking expectation on both sides, we get something like integral dt of integral over RD pt of x dx or dpt of x times dou by dou t p of t comma x plus grad phi of t comma x times v of t comma x plus half trace of sigma sigma transpose p of t comma x. Okay, now this is what we call the Fokker-Planck equation. Okay, so last time what did we do to when pt is a smooth density? Yeah, sorry, it's a Hessian of phi. Okay, so last time what did we do to get a PDE which involves only p when it exists? Correct. And then correct. So basically what we do after this is that we apply, whenever it's a smooth density, we go and apply integration by parts, and then we can exchange this summation, we exchange the derivative from here to here, use the fact that they vanish at 0 and at infinity and so on. So this would imply 0 is equal to integral phi of t comma x times dt times dx times this whole thing, so which is dou by dou t p of pt of x plus gradient divergence over x of pt of x times v of t comma x minus summation I comma j where okay. So this is the equation we get. Again, I'll leave this as an exercise because it is just a simple calculation, but a little tedious to do on the fly here in the middle of the lecture. So therefore, we have this. This follows from integration by parts. Okay, and we have this. So this holds for every function phi. So therefore, this term must be 0. Right, when it is nice enough and smooth enough and so on, right? So therefore, this being 0, this is called the Fokker-Planck equation. Oh yeah, that's, you're right. It is Dij. Yeah, this is the correct. This is the Fokker-Planck equation. Okay, so here you have an extra term, which is this term. This is a second order term. If only this was 0, this was just a continuity equation. Yeah. Yeah, it is correct. This has to be minus. So because if you, whenever you do interchange one variable in this, you get a practical negative sign, but you do it twice here because the second order derivative. You have a Hessian and the derivatives have to go the other side. So, okay. So now we can see what this means. This all seems a bit abstract at this point. So let's actually see a few examples of what happens to the Fokker-Planck equation for some of the very basic kind of stochastic differential equations. For this whole talk, I will take this sigma to be for this whole series. I'll take the sigma to be like constant. Okay, it doesn't vary with space or time because we won't be needing that for the diffusion models. Okay, so now we have something like let's say example 1. Okay, dxt is equal to dbt, right? So you can so here v of t comma x is equal to 0. Sigma of t comma x is the identity matrix. Okay, so then you can apply the Fokker-Planck equation. Then the dou by dou t of pt of x is equal to Laplacian of pt of x. How many of you know what a Laplacian is? Okay, so let me actually quickly define it. Laplacian of this is defined as summation I equals 1 to d. Okay, so what is this equation called? This is a very famous equation. Yeah, it is called the heat equation. Okay, so given P0, do you know, so can you give me a solution for this for all t greater than 0? I'll tell you a density or a probability measure at t0 or t equals 0. That is, I will give you an initial value problem. How do you actually solve this at arbitrary time? No, there's a closed form answer. Something like this, yes. So I think 4t, if I remember correctly. So if you should have actually pt of x is equal to integral over dy e to the minus mod x minus y squared by 4t divided by 4 pi t square, sorry, 4 pi t to the d over 2 p naught of y. Right, so this is the solution to the heat equation. Yeah, I'm pretty sure this is the solution to the heat equation. So what this is doing is this is basically Gaussian smoothing the original thing. So as you can see, this is the Brownian motion. You kind of add a Gaussian to whatever you started with, right? So this would come up if I had root 2 here. Yes, you're right. Okay. So if you have dou by dou t of half delta pt, you get this. Right? This would be again a half here. Okay. So we can now consider the main chain we'll be dealing with for the diffusion model. This is called the Ornstein-Uhlenbeck process. Okay. So here you have dxt is equal to minus xt dt, okay, plus root 2 dbt. Okay. So here the Fokker-Planck equation is actually, okay, it's a very hard to make it intelligible just by staring at it, but let me write it for the completeness sake, which is dou pt by del t of x plus divergence of minus x times pt of x is equal to Laplacian pt of x. So here there is no root 2. Okay, so this is the Fokker-Planck equation. Here we could see that the solution to this SDE, the strong solution would be like, can anyone tell me what is the strong solution to this? dxt is equal to dbt if you integrate on both sides. You haven't specified the initial value, x0. So this, the solution to this is xt is equal to bt plus x0. So that's the solution to this. Okay, because we will need the initial value for the problem. This is very important. Okay, so similarly, let's actually integrate this using Ito's formula and see what we get. Okay, okay. So let's take phi of t comma x is equal to e to the times t times x. Okay, I understand that this is not a compactly supported function, but you can use convergence theorems to actually show that it, even if it's nicely differentiable, but and its expectations exist, you can also apply the Ito's formula. It doesn't have to be compactly supported. There's something like dominated convergence would give us this. Okay, so now let's apply Ito's formula to this function. So what do we get? Phi of t capital T comma xt minus phi of 0 comma x0 is equal to integral so dt. So the first term would be e to the tx xt. The second term would be the second term would be e to the t times minus xt, as you can check it out, because the drift is minus x, right? And plus you get root 2 dbt. Okay, and the second order term is 0 because the Hessian of this phi of t comma x is 0, right? Okay, so now right, so what does this mean? This would be no, grad phi is, no, so yeah, e to the t dbt. This is correct. Okay, so we have this equation. So now let's actually expand this out. We actually get a closed form expression in this case. You have e to the t xt minus, e to the 0, x0 is just x0. Okay, this cancels out, right? This becomes 0. This must be equal to square root 2 times integral e to the t dbt 0 to t. Okay. Okay. So now this implies xt is equal to e to the minus t x naught plus square root 2 e to the minus t integral 0 to t e to the t dbt. Okay. So by definition of Ito's integral, can someone tell me what should this distribution be? What family of distributions would this be in? And this one? No, it's Gaussian actually. Parth is correct. So why? Because sum of Gaussians is a Gaussian, right? And how did you define Ito's integral? It's by linear combinations of Brownian increments, right? Linear combination of Brownian increments must be Gaussian, and all L2 limits of Gaussians is a Gaussian. So this must be a Gaussian. Okay, we can actually easily calculate the covariance of this thing, and that would turn out to be e to the minus t x0 plus standard normal distribution of 1 minus e to the minus 2t times identity, right? So I'll leave it this computation of this variance of this as an exercise. In fact, to do this calculation, we don't even need Ito's formula, this Ito's integration. We can do with something much older called Paley-Wiener integral, right? There, that exists because you can always, if this is a continuous function, this has finite local variation, so you can just integrate a function like this, and it just exists. And Paley-Wiener integral always leads to Gaussian kind of an integral. This is a Gaussian random variable, right? Where the problem started for us was that when we were trying to integrate random variables, which could also not be finite variation against Brownian motion, that's where we had to do the martingale trick to actually construct it. So, but this can be done with a Paley-Wiener integral. Okay. So let's stare at this solution for a bit. Let me actually go to that side. Yeah. No, there's no Hessian. Hessian is 0. There are 3 terms in Ito's formula. So there are 4 terms in Ito's formula, right? There is this, no, there is this term. This term is 0, Hessian is 0, and this term is what I wrote. So of course we have the OU process, that is dxt equal to minus xt dt plus root 2 dbt, and xt for every t, we saw that this was e to the minus tx naught plus some normal random variable times 1 minus e to the minus 2t times identity. Okay, but very importantly, I can't just sum two random variables like this. We need to show that these two are independent. Okay, whenever the initial condition is independent of the Brownian motion, these two are independent random variables. Okay, so let's try to make sense of this. Okay, what is the first part? First part is decaying exponential. Okay, so I asked you, what is the solution of this ODE? E to the minus t x naught, right? So this shows up here. It is trying to decay to 0. Okay, but then you're adding this Gaussian perturbation, right, which is preventing it from going to 0 by adding this kind of noisy paths to it. right? So therefore you get a normal random variable on top of this. Okay, so eventually as t tends to infinity, okay, this converges in distribution to a normal random variable. Okay, so we call this the stationary distribution of the OU process. Okay, so if I start with the data distribution as x naught, okay, this is a good way to destroy information. So I'll just take this, I'll multiply this by e to the minus t and add a Gaussian noise of this nature, and then I've destroyed the information in my image, and which is the opposite of generative modeling. Okay, so there's an old saying that opposite of love is not hatred, it's disinterest. So this is also not the opposite of generative modeling is not destruction of information. Okay, but we can hopefully reverse this from this, learn some lessons from this. Okay. So now we had let's see how to reverse something in general. For that, let's actually just look at the humble ODE. So we have dxt by dt is equal to v of t comma xt. Let's say that's all we have. So if I actually make a video of a particle moving in this velocity field, time t equals 0, it's somewhere here, and at time t equals capital T, it's somewhere here. Okay. Now I'll take y t, I'll define it to be x capital T minus small t. Okay, what does this correspond to? This corresponds to playing the video in reverse. Okay, this I suppose I reverse this chain. So initially I started with noise. I started with signal. I went to noise. Now I want to start with noise and go to signal. I just want to reverse the video which I took of this motion. Okay, so what does this satisfy? Any guesses? Huh? Sorry. Why not? Or correct. So what this satisfies is dyt by dt, right, must be equal to minus v t minus t of yt with y naught is equal to xt as the initial condition. We can actually solve this initial value problem. Yeah. Sorry. This is x, right? Xt versus t, right? Solution to the ODE versus time. Right? Let's think of it as a Monday. Okay. So we reverse the direction of the velocity and we reverse the time, and we actually go from reverse the ODE solution. Suddenly we had some destructive process which destroyed the image we started out with, and now we have a constructive process which will start with noise and give us back our image. And this is the principle behind denoising diffusion probabilistic models, aka diffusion models. Okay, so I try to give a fairly rigorous treatment so far. But from now on, I'll take more empirical CS kind of approach and try to give intuition as to why diffusion models work, give some calculations, and give you algorithms for training diffusion models. Okay, so right. So now, but okay, you might say, okay, we destroyed information with this Ornstein-Uhlenbeck process. We didn't really have an ODE. How do we actually, reverse this kind of a Markov chain? So I want to say that the solution to this is a Markov chain. I won't go into explaining why it is or what it is, but take my word that it is. And every Markov chain, under fairly general assumptions, if you time reverse it, that is also a time-dependent Markov chain in general, right? So this is because of the Markov property, and therefore reversal of this. Suppose I start with a large T, capital T, which is approximately Gaussian, and if I time reverse it to generate the original image, then that is also a Markov chain. Okay. So let's try to derive what is the drift and diffusion coefficient we might require to make that happen. Okay, so the rigorous derivation of what I'm about to derive actually requires Girsonov's formula and Dub's H transform, which we won't be dealing with now. I'll just use a more intuitive approach, which does not actually show that they are reverses as Markov processes. I'll just show that we can reverse their trajectories in the space of probability distributions. Okay, so that is my goal. Okay, so now we had this equation. Let's actually look at this simple systems Fokker-Planck equation. So we had dou by dou t pt of x plus divergence of vt of x pt of x is equal to 0. Okay, so now I'll define qt to be the law of yt, which we know should be equal to p capital T minus small t. Okay, can anyone guess what continuity equation this should satisfy? What continuity equation qt should satisfy? Yeah, correct. So what this satisfies is, we know that of x minus divergence of vt minus t of x qt of x is equal to 0. I mean, this is just very simple, because just because yt follows this ODE, this continuity equation must hold, right? And if that continuity equation holds, then we know that we can get back this kind of an ODE as it as a push forward of this kind of an ODE, right? Where we kind of saw these results. I didn't prove it, but we saw it. Okay. So I told you there was a very, very deep result in the theory of Wasserstein flows and Wasserstein geometry, that almost any dynamics with reasonably continuous dynamics in the space of probability distributions satisfies the continuity equation, right? Do you remember this? Okay. So I will take my word for it that if you look at the law of PT of this Ornstein-Uhlenbeck process, it is a very nicely behaved trajectory in the space of probability distributions. So the Fokker-Planck equation for this must also satisfy the continuity equation with some other velocity. Okay, so let me actually demonstrate that. So this must also satisfy a continuity equation. And this is in addition to Fokker-Planck equation. Okay, yeah. For continuity equation. Okay, that actually uses the fact that if you have a curve in the Wasserstein space, which is uniformly, absolutely continuous in the Wasserstein distance, then you can apply something called the Riesz representation theorem. And that actually gives you this. You have to massage the results a bit. It's a one-page proof. It's a very cute proof, but it just follows from Riesz representation theorem that it must hold. And you want to consider the Hilbert space. There is, the L2 space of 0, t times. Right? No. If you have mu t of x and times Lebesgue measure on. Okay, the measure on the space is actually you draw t from Lebesgue measure. Lebesgue measure and x from mu t after you choose this. So with this norm on the space, you actually apply Riesz representation theorem, then you can actually show that this satisfies the continuity equation after a bit of massaging. No, Fokker-Planck equation is generally of the form, okay, if this is what continuity equation looks like, Fokker-Planck looks like dou t by, let's say, pt plus divergence of vt pt is equal to something like, yeah, we know how to reverse the ODE. Okay, so, but we don't know how to reverse the Fokker-Planck equation in the randomness in the process. Correct. Yeah. Correct. which is similar to the Fokker-Planck equation, but that must also be satisfied. So continuity equations are of this form. Fokker-Planck equations are of this form. Process which satisfies an SDE satisfies a Fokker-Planck equation, but it must also satisfy an ODE called the continuity equation, or a PDE called the continuity equation. Correct. So that's what I'm saying. So no, but not the same continuity equation with a different drift. No, the same process satisfies Fokker-Planck equation and a continuity equation. I'll show you. You will think that it's trivial, but it is actually quite nice. It's a very straightforward thing. Okay, let me actually go there. I think this is too ODE-ish kind of board, so I'll take a fresh board and explain this. Yeah, correct. So this board, beyond this line is SDE, right? Whatever is here is for the ODE. There are different processes. May or may not be. That's the problem with the notation. Yeah. So in the Fokker-Planck equation, also should satisfy a continuity equation. Yeah, that needs to be resolved. Yes. Okay. Right. So now we had this OU process minus xt dt plus square root 2 dbt. Okay, this satisfied dou by dou t pt of x plus divergence of x pt of x is equal to Laplacian pt of x. This is the Fokker-Planck equation. Okay, so now what is divergence? Laplacian of x is equal to summation I equals 1 to d squared pt of x, which is equal to divergence of gradient of p, okay, which is equal to divergence of grad log p times pt of x. Okay, for t greater than 0, we know that it has a smooth density because it's a Gaussian convolution. Okay, all these things exist. Okay, so now we plug this back in. Okay, so we had this implies dou by dou t pt of x plus divergence of, I think it's minus. You just use this identity, push this on the other side, and you get divergence of minus x plus minus grad log pt of x times pt of x is equal to 0. This is continuity equation. Now I'll call this a continuity equation, exactly. But I know how to reverse this. No, okay, actually reversing the Fokker-Planck equation technically we would have to go to the Doob H transform. Correct. No, but okay, so we want to make a difference between the path space and the measure space. This trajectories of the solution of this ODE is purely in the space of probability distributions, but our thing is in a path space. So path space, if you want to describe a process, you need to describe all the finite dimensional marginals, right? But if you just showed me this, the solution to this could be generated by as a push forward of an ODE or as a push forward of an SDE solution, right? So that's my point. You can reverse this. Yeah, you can show. Yeah, you can see this as a solution to an ODE. I know how to reverse the ODE, and so therefore I know how to reverse this trajectory in the space of probability distributions. Yes, and it's not the same thing. It's with a modified drift. You get an equivalent continuity equation by modifying the drift. Right. So, okay, this is a very trivial way of seeing things. Like you said, it's a manipulation. But where it gets more interesting is that when you have more nonlinear terms, and even then you should have it satisfy a continuity equation with some velocity, and then it's not clear. but this is a relatively simpler thing. Okay, I'm taking this approach because I don't want to introduce Girsonov's formula and Dubs-L H transform and so on. Okay, so what is it? So now let's say Qt is equal to P T minus T. Okay. Question: what is the continuity equation for Q? Right, I just showed you this. So basically you reverse the sign of the velocity and then you take the time to be t capital T minus small t. That's what gives you reversal dou by dou t Qt of x plus something like divergence of correct. Yeah, I'm reversing the ODE to show you what is the path. Correct. Correct. Oh, okay. Actually, showing that the reverse XSD is a reversal in the path space, that requires much more deeper theorems. I'm not going to do that. I'm just going to hand wave that part. Okay. That's Anderson work. Exactly. That's Anderson work. So grad log Pt of x times Pt capital T minus T times Qt of x is equal to 0. See, because we retain this P T minus T and then you have this Qt here. So this must be the drift we require to reverse the process. We can actually do that. So we already have the reverse thing. You can add and subtract this quantity here. So and then you get a diffusion suddenly. Okay. So I mean actually I can write this as grad log Qt of x. Okay, you add and subtract a grad log Qt here. So this implies dou by dou t of Qt of x plus divergence of x plus 2 grad log Qt of x times Qt of x is equal to Laplacian of Qt of x. Okay, we got back a Fokker-Planck equation out of this. Okay, so now what gives rise to the Fokker-Planck equation of this form? It would be clearly dxt, let's call it reverse, is equal to xt reverse plus 2 grad log p t minus t of xt reverse dt plus square root 2 dbt. Okay, I just applied it in reverse and read back what SDE should lead to this kind of a Fokker-Planck equation. As a Markov process, is not, we don't know if it is this, but in the in the reverse direction, correct. But it turns out that this is actually the reversal, but I won't prove it. Yeah. Okay. So now this is what we need. So we had a destruction process there, which is this one, and we have a generation process here, where you take xt maybe as approximately a Gaussian random variable, and n of 0 comma identity, and then hopefully at x0 if you run this, x0 as this and xt, you would have a nice target distribution. Okay, so this is the mathematical core of diffusion models. Okay, so there's another principle which is the mathematical core of flow models, which hopefully I'll discuss tomorrow. Right? Okay, we have 25 more minutes. I'll actually tell you how to learn these diffusion models and write down the algorithm for it. Okay, so now we showed that if I start from a Gaussian in this stochastic differential equation and run it for time t, with some discretization, pick your favorite, Euler-Maruyama or midpoint method or Milstein method or whatever, and for time t, I'll end up with a target law. Okay, and it works quite well empirically as well. How do I learn this? What do I need to know to be able to run this ODE or SDE? Correct. So we need to know this quantity called grad log PT, right? And that is why we want to do something called score matching. Okay, so this is not, as many of you actually know this because you're trained in statistics. This is not this classical statistics score function from the parametric statistics kind of thing. This is a high variance notion of statistics, which is used to match to distributions by minimizing Fisher divergence, right? But this also turns out to be very important for generative models. So let's actually state the problem separately. Okay, suppose I have x naught from the data distribution. Okay, and for some t greater than 0, I define xt is equal to e to the minus t x naught plus square root of 1 minus e to the minus 2t times z, where z is distributed as normal random variable and z is independent of x naught. Okay, so this is the law of the solution of the Ornstein-Uhlenbeck process at time t. We integrated this using Ito's formula, and we can just generate this. We don't have to simulate the forward ODE. I'll just give me a t, I'll write down the solution to this. Okay, so now we know that xt is distributed as some pt. Okay, so the learning theory question is this. Okay, given samples, x0 of 1, x0 of 2 to x0 of n, estimate the functions, and these are, let's say, IID from some distribution P naught. Okay, estimate the function grad log pt of x for all t belongs to 0, t. Or maybe we can have an open set here. Okay, so this is what we call the problem of score matching. Okay, so given samples from a distribution, is there a question?
Why is the word matching? Like, what's matching here?
I have no idea why it's called matching. It's learning score. I mean, I think Haryana uses this word called matching in his 2005 paper. I mean, I guess he didn't use them, but it was also in a JMLR, like Journal of Machine Learning Research. So I don't know why he didn't call it learning. I guess, okay, so what he was trying to do was he was trying to match them in Fisher divergence, two distributions, by minimizing the Fisher divergence. And that reduces to matching their score functions in some sense. So that was maybe the reason. Yeah. Correct. You match the moments, and similarly you match the score. Yeah. No, but moment matching is a way to approximate distributions, right? Right. So that's like kernel methods. Yeah. I guess so. That makes sense. Okay. So yeah. So we have this thing called score matching. Okay. This using this to attempt and approximate distributions was started with Ivarinen in 2005. Okay, this is a JMLR paper. This is actually very nice and accessible. The algorithm Ivarinen used is called implicit score matching. That is, no. This is just some kind of an inference setting. So if you have some samples and you have a parametric family of distributions, right? Can you choose a parameter which fits this distribution the best? So that's yeah. Yeah. Huh. No, I mean, the techniques actually go back to a long time. Actually, there's a very nice talk by Arnaud Doucet in NeurIPS 2024. It's an invited talk. He gives a lot of overview as to how it did. So the reversal of these processes are very, very long known. Even the flow matching, which I'm going to present tomorrow, it has been studied by mathematicians. It has been studied by physicists. They call it some kind of Markov projection or something. And reversal of stochastic process is also a very classical topic. Generate images, that was started in Max 2015. Maybe there were some elements of this, and 2020 was when it actually. No, I think there were a physicist and a non-physicist, many non-physicist computer scientists on it. So I think Surya Ganguly was on it, I think. He was a physicist, you know. Yeah. So that is something, but yeah, I don't know if you would call it that, but they did have a non-equilibrium statistical mechanics to this, but it only had elements of what we call it now. The actual solidification of that took place much later in 2020-ish. Yeah, the Fallmer drift and so on, right? No, that's not it. That's different. Yeah. No, but the reverse form is actually very classical. It's also well known. There's a paper by Anderson in 1980s, I think. Yeah. Yeah. But reversal of a Markov chain being a Markov chain is OU. Yeah. No, not just OU. Any SDE. You can reverse as in reasonable. Any reasonable stochastic differential equation, you can reverse it as a Markov process in the path space. And I can send you the reference. It's Anderson 1980s sometime. Correct. Yeah. On any. Yeah. Exactly. So all Markov chains are reversible, but as time-dependent Markov chains in general. Yeah. So, okay, this uses something called Hyvarian and uses something called implicit score matching. Right? So that actually involves second derivatives of things, trace of things, and it's actually very hard probably to make it work with neural networks. I think people tried in 2018, 2019 to do generative modeling by doing some kind of estimation of the sort. They came up with slice score matching to actually do away with the problems of implicit score matching, but it was ultimately not very successful. What we actually do these days in practice is something much simpler called denoising score matching, which follows from Tweedy's formula. Okay. So the next part of this recipe is this. Okay, this is the aim we want. We want to do score matching. So I'll introduce some important theoretical results to be able to do. Okay, how many of you have heard of Tweedy's formula? One. Okay, one person is two people, three people. Okay. Three people have heard of Tweedy's formula. So suppose y, z are independent random vectors in Rd, and we define y prime, another random variable is defined by y plus z. Okay. So question 1, what is expectation y prime given y? Yeah. Okay. And yeah, right. So let's now assume that z is, yeah, it is just y. Okay, you're correct. Okay. Second question, what is expectation y given y prime? This is a harder question. So now let's think of this problem a little bit. Okay. So we are given, actually this ground truth is y, you add some noise to it. Okay. And then you make an observation. Okay. So then what is the original value, expected value of the original, given that you see a noisy output? Let's actually add a sigma here to make it a bit more non-trivial than that identity matrix. Okay. So you actually see this. Okay. You see a noised version, and then that is, you condition on that, and you want to find the best unnoised version of this. Why is a random vector? They're both independent random vectors in Rd, and z is distributed as a normal random variable. Okay. Actually, this is not an easy question. There's a thing called Tweedy's formula which will actually tell you this. The answer, let me tell you, is actually equal to y prime plus sigma square grad log p, let's call it py prime of y prime. Okay, sorry about the abuse of notation. I just want to show that this is a density function of y prime. Okay. Okay, so now you can see why I want to make use of this formula to do score matching, called denoising score matching, because there's a nice conditional expectation here. Huh? Z is Gaussian, yeah, I'll derive it, yeah. Yeah, but there are some other score matching techniques called target score matching. This was again 2 years ago or 1 year ago paper. I can send it out, but this won't work. Yeah, as such doesn't have an answer. Only Gaussian said this is very nice. But tomorrow we'll see in score matching that it doesn't need to have a nice formula. Sorry, flow matching. We see that it doesn't need to have a nice formula. You just learn this conditional expectation. You're good. Okay. So, but okay, that's for tomorrow. Okay. How are we going to prove this? Given that all the proof techniques I've used so far, how do you think we're going to prove this? If you have been listening closely, the only thing we've used is integration by parts. We're going to use integration by parts. Okay. So okay, so Tweedy's formula follows by integration by part. Actually, no. Yeah, that is exactly Tweedy's formula. Okay, so now actually let's take a look at we have y prime is equal to y plus z times sigma. So where z is distributed as normal of 0, identity. Okay, so now let's actually consider expectation z over sigma squared, or minus expectation of z over sigma squared. I mean, given y prime. Okay. Now, this is equal to integral minus z is y minus y prime. Actually, over sigma over sigma times e to the minus, I think I made a mistake here. Yeah, this is correct. E to the minus y prime, p of y given y prime dy. This follows from the definition of conditional probability. Right, yeah. No, is this correct? Why is it sigma? This is correct, right? Yeah, so there should be a sigma squared here. I made a mistake there, but yeah. Okay, this makes complete sense. Okay, this must be equal to integral y minus y prime divided by sigma squared. Okay, we apply Bayes rule to this. Okay, p of y comma y prime times divided by p of, let's call it py prime of y prime. This is just to show that this is a density of y prime. Okay, and times dy. Okay, so again we use the Bayes rule again. So or definition of conditional probability again, divided by sigma squared. We know what is p of y prime given y. It's just a Gaussian measure because it's just a Gaussian addition convolution to that. So this must be, okay, we'll actually do y minus y prime divided by sigma squared times p of y prime given y times p of y dy divided by py prime of y prime. So this is abuse of notation just to show this is the density, but these should be treated as probabilities. Okay, so now this is the Gaussian density. Okay, so we'll write as integral y minus y prime divided by sigma squared e to the minus y prime minus y squared divided by 2 sigma squared divided by 2 pi sigma squared to the power d over 2 times p of y divided by py prime of y prime times dy. Okay, so now what will we do here? This is basically a derivative of this. Derivative of the negative of the derivative of this with respect to y prime. Okay, so this is equal to d by dy prime of e to the minus y prime minus y squared divided by 2 sigma squared divided by 2 pi sigma squared to the power d over 2, and then we have this times p of y divided by py prime of y prime dy, and you have an integral. Okay, so now we can obviously take the derivative out because of what formula, integration by parts, and then this will be d by dy prime integral d by dy prime divided by py prime of y prime e to the minus y prime minus y squared divided by 2 sigma squared divided by 2 pi sigma squared to the power d over 2 p of y dy. Okay, this quantity, as you can see, is a Gaussian convolution of the original distribution of y, unnoised y. So therefore, this must be equal to py prime of y prime. So this is equal to d by dy prime of py prime of y prime, and this divided by py prime of y prime, which by our first course on calculus, this is actually equal to grad log py prime of. This actually proves the PDE's formula. How much time do I have left? Okay, I have 5 more minutes, so I don't think I'll have the time to do much else. Okay, then I'll do one last lemma. So I hope the PDE's formula is actually clear. That is the theorem I've written there, and that will tell us how to learn it. Okay, so now let's actually bring this to back to the learning theory setting. We've expressed the score function as a nice conditional expectation. Okay, how are we now going to learn this conditional expectation? So here's another fundamental theorem from statistics. Okay, so suppose, let's say y comma z are, let's actually think of x comma y are jointly distributed random variables. Over, let's say, Rd. Okay, so let's say we have a function f from, we consider any arbitrary measurable function from Rd to Rd, and then we consider the following optimization question. Argin over all f measurable expectation over x comma y of norm f of x minus y squared. Okay, so let's say this f star belongs to this set. What is f star? Okay, can you tell me anything about f star? Exactly. So yes. Okay, the answer is f star of x is equal to expectation of y given x equals x, where within the essential whatever of the distribution x. Okay, so this is the answer. So we actually make this connection. We have this. We know how to solve this as an optimization problem. What we do with neural networks is solve optimization problems, and we have this conditional expectation problem score function popping out of learning a conditional expectation. Okay, so now we'll put these two things together and learn diffusion models. Okay. Okay, so we have, let's say, H is a class of function approximators, let's say f from 0 to comma t times rd to, let's say, rd. Let's, for clarity, let's take this. Okay, so let's think of this as neural networks of some architecture with some weight class and so on. Okay, we are given some data which is x of 0, which is from the target distribution from the target distribution P naught. Okay, we construct the loss function. Okay, what will we do? We integrate 0 to t, and we have dt. Okay, and summation I equals 1 to n, norm of f of t comma xt of I plus z t of I divided by, actually, let me write this in a more tractable form. Okay, so now for each, let's say t belongs to t1 to t capital N. Okay, so we will generate the following. So x t I is equal to e to the minus t x naught plus square root of 1 minus e to the minus 2t z t I. Okay, so xt naught I. Okay, so that is, I'll take the ith sample and I'll add Gaussian noise to it. Okay, and then that's how I get xti. Okay, so now I'll form the loss function L hat of f is equal to 1 over n times n summation t, summation over t belongs to this finite set t. Let's call this set as t. Okay, norm of f of t comma xti plus z t I divided by 1 root of 1 minus e to the minus 2t squared. Have I? Yeah, I don't think I'm using I multiple times. I is the sample index. You're given n samples. And I've used just t for the indexing of this. Yeah, I should also sum over the samples. I equals 1 to n. Okay, okay, what did we do from here? We know, okay, we can solve this in expectation. If we solve this, we know this, but we cannot have expectation. We just replaced it with empirical expectation of this, and I know that I can't minimize over this class of all measurable functions, so I just plugged in a neural network or something. Which jointly parameterizes time and space. It takes a time and it takes a point in space, and it will try to learn gradient log pt. Okay. So therefore, what does our learning algorithm do? It tries to get argin. F belongs to this nice class of functions, L hat of f. Okay, I mean, of course, they won't actually get argin of f. F belongs to S. They'll use some SGD or Adam kind of optimization algorithm, get a good enough local minima, and then just plug it in. Okay. So yeah, this is how you train diffusion models. I think this is a natural point to end the third lecture.